A buck regulator is a step-down regulator that converts a DC to a DC voltage. Now the supply voltage is E and the output voltage is V out, and it has got a switch that is operated at a high frequency, and the duty cycle of the switch, that is the ratio between the time that the switch is on and the period of the switching, determines the output voltage. So we can see that there are two modes of the circuit, two equivalent circuits. So if we go to, say, mode 1, when the switch is closed, we will have a circuit that looks like this. And the moment that the switch closes, that positive is placed on this cathode of the diode. And the diode is in the reverse biased and switches off, so it is not in the circuit. We still have our inductor, and we have our capacitor, and we have our load. So the current that is flowing through the inductor here is IL. The current flowing into the capacitor is IC, and the output current is I out. So once more we have IL, IC, and I out. And that's in mode 1. In mode 2, the switch now opens, and when the switch opens, the inductor reverses its polarity. And so where previously in this mode it was positive, negative, now the inductor polarity will be negative, positive according to Lenz's law, and that will place a negative on the diode's cathode, and it will forward bias the diode so that it switches on. And once more we have the capacitor, and we have the load. IC, IL, I out, and V out. And this is mode 2. Now the voltage over the inductor, VL, is the difference, in this case in mode 1, between the voltage E, which is placed there, and the voltage V out, which is there. So we have E and V out. So in mode 1, VL is equal to E minus V out. And in mode 2, VL is equal to 0, and we still have V out on that side. So it is 0 minus V out. Now what about the current flowing through the inductor? Now the inductor is a component that is placed between the input of the circuit and the output section of the circuit. So the average current that flows through the inductor will also be the average current flowing out of the supply and the average current flowing into the load. Now there is two ways that we can operate the switch. The one is the continuous conduction mode, and this refers to that there is continuously current flowing in the inductor. The other one is the discontinuous conduction mode, which means that there are sections in which there is no current flowing through the inductor. In this course, we will not be looking at the discontinuous conduction mode. We will be looking at the continuous conduction mode, because that is the most prevalent way in which the buck regulator is used. So looking at the inductor, we know from ways gone by, or days gone by, that V is equal to L di dt. So this E minus V out during the time that the switch is closed is equal to the size of the inductor multiplied by the slope of the current through the inductor during the time that the switch is closed. So if we go and look at a graph, and we look at continuous conduction mode, where this is T, that is the period of the switching, and this is equal to KT, we can get the slope of the current through the inductor during this time here, because this is T and that is I. And the voltage that corresponds to this slope here will be positive, since this slope here is positive. And the voltage that corresponds to this negative slope here will be negative. So if we go and we sketch this waveform here, we'll see that it will be positive there, where this is VL, and it will be negative during that period there. Now we have a voltage, a current value, the I peak, which is common to both the time that the switch is on and the time that the switch is off. So if we can get an equation for IP during the time that the switch is on, and we can get an equation for the time that the switch is off, then we can eliminate IP and in that way solve for a transfer function which shows us the ratio between V out and E, and if we denote the switching or the duty cycle of the switch as K, then we can solve for a formula that will give us the output voltage for any given input voltage if we know what the duty cycle of the switch is. Now the duty cycle of the switch means that it is, this is the duty cycle, K is equal to V out over E in the case of the buck regulator. And we would like to derive this ratio here because this is also the transfer function. So what we know is that V out over E is the transfer function, and we want to show that it is equal to the duty cycle K, where K is equal to T on over dt. So taking mode 1 and from the VI relation of the inductor, we have that V is equal to L di dt. Therefore, V dt is equal to L di. So if we place an integral sign on both sides, and we see that for t we have the limits 0 and kt, and for I we have the limit 0 and ip. Now there is no t in v, so v comes out to the front. So the integral of 1 dt is t, and the limits are 0 and kt. The same happens on this side. 1 di is I, and the limits are 0 and ip. And therefore, we can say that V kt minus 0 is equal to L ip minus 0. Therefore, KTV is equal to LIP. Therefore, IP is equal to KTV divided by L. But we've already said that VL is equal to E minus V out during mode 1. But V is equal to E minus V out. Therefore, IP is equal to E minus V out KT divided by L. And that gives us equation 1.